Hello everyone, this is lecture 9. We need to move on and start doing some more advanced materials. The idea is that we could at some point discuss files, arrays, maybe recursive functions, and dynamic memory allocation. Let's start with files. First of all, files are a concept of the operating system. It's something that operating system manages. Without operating system, there is really no files. You can have a disk as a piece of hardware. You can even have a program that can have access to this whole disk. But usually, when you start splitting the space of the disk into separate fragments, that's already dealing with files, basically. Sometimes I heard about some databases, they're custom-made databases that do not use files at all. For databases, it's much faster to access the raw disk. It doesn't happen very often. It's not a normal, common thing, but one can use a disk without really creating any file system on the disk, without writing any files. So you have your disk, use the whole disk as you like. We will be doing files, and we will start by looking at the files from the command line perspective. We will first list the files in the directory. I will put an argument -1 like this. So this is the contents of my directory. And what I can do here, I can do the same thing, but put the greater sign, and then output the output into a file. Let's call it my list.txt. Something happens, nothing is printed, but now we have a file which we can print out. And indeed, it contains the result of the ls command. What can be done else? We already used an echo command. And we will add a line, but now this time we will use two symbols, greater, and this will mean to append to the file. This is the portion of the operating system that's called the shell. It's a program. Usually the program is called bash, but not always. And this is the program that you're currently interacting if you're running a Linux terminal. Bash allows you to run small, simple scripts, and one of them is to redirect the output of some program into a file instead of printing it out on the screen. So this is what we are doing right now. Let's again print out my list.txt, and indeed there is a hello file line appended. When we ran ls command, we added an argument -1. This argument changed the format of the output of the command. It, instead of making several columns, it just made a single column list of files. What we are going to do now, we're going to write a Fortran example that would take an argument. We will have this character string that will eventually contain this argument. We will call it argument number string. We'll give it the size of 20. We will also have an integer, and the idea is to take a string, which we will assume is an integer, receive it, and convert it into this integer and then do some mathematical operations with it. So there is a built-in function that's called command argument count that gives you how many arguments the user passed to your program. We'll do this. If it's not equal to 1, then we stop. And then there's a new command for you guys in Fortran. Stop means that terminate the program. There's another option to do that, just called call exit. It turns out there is a keyword stop, just terminates the program. So if we passed this portion of the code, so if there is indeed one argument, we get it. So we call the function get command argument. We get the first argument and copy it into the argument number string, which is a variable, but it's a variable that contains a string. And so now in this argument number string, we have a string, but it's not a number yet. It's a text string. So we convert it by invoking the read function. But now instead of reading from the star, remember there was this mysterious asterisk parameter that we always used with read. It can be replaced with a string, with a name of the string variable. So this is what we do. So we do read from argument number string. Then we supply a format to read, which I think it's not absolutely necessary in this case because we will only pass it integers. And that's our format for now. And we will write the result into start value, which is now an integer variable. All right, so not just integer, but an 8-byte integer. And that's it. So we then output what we had in the end. So we output this integer start value. And just to ensure that we can do mathematics on it, we output the same start value plus 1. Let's run it. If no arguments, it will stop. An integer number should be provided. Let's give it an integer number, 1, 2, 3. And the user entered 1, 2, 3. Plus 1 will be 1, 2, 4. Now we will, of course, apply this new knowledge to our previous example from the previous lecture, the callouts example. Of course, the idea is to supply the starting value for the callouts algorithm. The starting value will now be supplied as part of the command from the command line interface as an argument. So the code stays pretty much the same as before. The same next element function. What changed is we kind of merged it with the example that we just saw. So we will now have argument number string. We will receive this string using the get command argument. We will convert it into start value. And we will loop this next element function. We will do this callouts conjecture steps to produce that sequence until it reduces to 1. Again, callouts conjecture is not proven. There might be a number that never goes down to 1. People searched, they didn't find any just yet. So in our case, we should not be worried that our algorithm will go into an infinite loop, because we're just not gonna do this large enough numbers, and maybe there's none that give you an infinite loop. But let's look at this do while loop. It's also changed a little bit. We will print out the value first. We will use this new interesting format string I0. So this is not IO, this is I0. And what it will do, it will adjust the width as needed. Why we using write? Because we will not get a new line. We'll just print all the sequence in a single line, in a single string. We'll separate them with commas. And when we're done, when we reach 1, at the end of this sequence, we will write that 1. Because when we reach 1, the loop will no longer execute, and the previous value that we had would be 2. So we'll just add 1, just so that we don't have the comma hanging at the end of this list. Let's run, say 10,000, and indeed a sequence is produced. Let's write it into a file. We'll use the file result, and indeed that file is created. Let's print out the file. You see where I'm going with this? I promise you it's going to be interesting this time. All right, so it is in the file. Now what we can do? Let's look at those shell script files that are already prepared. Script1.sh. What does it look like? So this is not a Fortran program, it is now a shell script. It's another programming language with which we program Bash, which, as we talked, it's the program that runs while you are in the terminal. So it has its own shell script language. I'm not a specialist in that. I can only do very basics. I never thought I will ever need that, but sometimes for scientists, yes, maybe. That knowledge never hurts. Let's do a few things. So first is the comment line, but it kind of tells you what this file is. It is a bash script. I think this is the meaning for this line. Maybe I'm wrong. Let's look at the code itself. There's some sort of do loop. It starts with a 4. I is the name of our variable. It will go from 2 to 10. And then the loop goes like this. Starts with do, echo, welcome, then the variable, and done. So it's similar to the Fortran do loops, it's just different syntax. Let's run the script. By the way, before you can run the script, you'll have to write a command chmod, change the mode, actually chmod, change mode, and plus x, and then the name of that script1.sh. It runs. It will make it appear green if you list those files. This bright green means that it now has an executable parameter. You can now execute this file. Let's execute. So /script1.sh. And indeed, it does what we intended it to do. It echoes, it writes into the terminal the variable, and the variable goes from 2 to 10. I think another way to execute those scripts is to just invoke sh. I don't want to appear unprofessional here. I'm not a specialist in that. I kind of know the idea about the scripts, but I just don't use them very often. Script1.sh, and indeed we get the same result. So that's another way to run them. Guess what we are going to do now? Let's look at the second script, what it's intended to do. First, this line, so kind of like no command, and then just like greater result.txt. What does it do? Let's print out right now our result.txt, and it has the sequence that left from the previous run. Let's look at what this command will do. Greater into result.txt. What it does, it sends nothing into that file. Now let's print it out. That file still exists, but now there is nothing in there. Let's run this script, script2.sh. And as we see, it will execute the same loop, but instead of doing the echo command, it will run callouts with this number that ranges from 2 to 10, and it will append the results into the file. Let's look at the results, result.txt, and indeed we have now 9 sequences from 9 runs of this callouts program that we wrote. So right now we're kind of using trickery to create the file. We're still printing into the terminal window, but we're instructing the operating system to redirect whatever appears in the terminal. We're instructing to redirect into a file, result.txt, and append it at the bottom of the file. Moreover, we do a loop and we instruct the operating system through the shell script to invoke the callouts program several times. Now, of course, it would be interesting to experiment, to push the boundaries a little bit. Let's see how much the operating system can handle. Let's look at script number 3, script3.sh. And indeed, the script 3 is pretty much the same as script 2, except that we will be running callouts from the starting point of 2 to 30,000. So let's see how long it will take and what it will do. Moreover, there's a way to kind of run this program in the background. Terminal window will still kind of host this program that we run. So the program will be attached to the terminal. Whatever it outputs will go into the terminal. Because we redirected the output, nothing will go into the terminal. The point is, though, we can run this in background by adding an ampersand symbol. So like this, script3.sh space and then ampersand. And this is very important right now. So this program will be moved into background, and in the background it will run, but our terminal will be free for us to use again. So this actually displays the process number 25138, and let's run htop. It's a program that shows what's currently running on the system. First of all, we see that we do have some loads on the processor cores. There is also some users that are logged in and they're running something. None of them really uses the CPU, so everybody's CPU use is at 0. We will keep scrolling. This is me over here, and indeed there is a bash script which takes away from the CPU, so we are computing in the background. Now let's do even more interesting thing. Let's exit entirely. Let's log off. Let's exit as much as we can. Where basically, if we wanted to, we can close even all the windows and reopen Cygwin from scratch. So now we're completely disconnected from that Garfield system. Let's connect back and we'll invoke htop to see if our code is still there. So something is running. So we're running bin bash script3.sh. So we do have this background program and it's still computing. It takes away processor time right now from that machine. Thankfully, that machine, it's not really used that much. It's okay if we use it for something. This is academic purposes. So for now, we will just wait until it completes.
10 years later.
All right, so our bash script is done. Calculated 30,000 values minus 1. And we exit htop, nano result. And let's look at the file. So indeed, the results start with from 2. And we can scroll and scroll and scroll. Let's just go to the end of the file and it finishes with 30,000. So it ran this command 30,000 times until it reached that sequence. So we actually generated quite a lot of sequences. What should we do with them now? I don't know. One potential difficulty that you can already kind of like maybe sense with this is because all of these sequences have different length. Each of them would require an array to hold the numbers, but each will be of different size. So we cannot really make one big array to put all the numbers in there. Rather than for each tiny sequence, we'll need to allocate as much space as the sequence needs to hold it. So we'll have a very, very strange data structure if we try to use this file somehow. I'm not yet sure if we're gonna do anything else with this file. Definitely would be an interesting exercise to try to somehow load it and process it. But for now, we'll just leave it the way it is. The point of this was to show how to create files without really writing the code to create files. So we would just have the code that outputs something, but we can output this into the file. It seems like something that you would never really use in your life because everybody already is used to like Windows and we're using Microsoft Excel and we're using Notepad and things like that. But for the scientists who used Unix, who contributed to developing Linux, this is a very useful tool. One of its possible uses is to take some older code, but you can easily now take that output and redirect it, either write it as a file as we just saw, or even redirect to another piece of software for further processing. A couple of examples of that. Let's run something, very simple command, ls cpu. So we will list the CPUs that we have in the system. But now let's say we want to filter the result somehow, and we'll do this ls cpu vertical line grep. In this case, we'll just search for, let's say, megahertz, so MHz, and immediately we are left with just one line. So out of this large input that we had, we process it through grep, and now we have converted that output. I'll see you in the next portion of the video. For now, I am making a pause. You can make a pause if you'd like. Let's do another example, and I want to show it while my memory is still fresh. It's an example of writing a binary file. We will be working now in Windows in the Code Blocks IDE. To set it up, I had to install MinGW, I think, MINGW. You don't have to set up it the same way. I'm just trying different ways to compile Fortran code. Eclipse will work fine. Command line will work just fine. Okay, so let's look at the program. Here it's called binary file example. There is something now called file unit. It's kind of an arbitrary number that you select, but if you have more than one file open in your code, then those file units have to be different. So it's sort of a constant that defines the current file that you're working with. If you open a file, then close it, then you can reuse the same number, that same unit. We're gonna start with a smaller example first. It still has the same file unit. We have two values. One is the real variable, another is an integer. Both are 4 bytes in size. Real is just some random 55.5. The integer value, it's more sophisticated. It has this unique sort of negative number, but if you look at it in hexadecimal, it will look like code cafe. So C0DECAFE. It's easy to spot because it spells code cafe. Now we will open the file. The parameters that they pass to the open function are the following. So file unit, just some number that you selected. We selected 51. File name. So for this, it's one real dot dat, so like a data. It says form unformatted, access direct, RECL. I think what it means, it's the length of each record that you're gonna write into the file. So in this case, each piece of data that we write is 4 bytes. So our record length is 4. We just call one write function just once into this file unit that we just opened. Record location 1. So that would be the location where the byte is written, starting from 1 at the beginning of the file. And we write the real value first into the file one real, and then we close the file. And similarly, open the file one int. One just means that we're gonna just write one integer in there, and do the same for the integer. Now Control F9 for me to compile, Control F10 for me to run. Let's look at the results. We have one real and one int. Let's look at the one int first. Now this is some strange gibberish, but if we look at hexadecimal, we can see code cafe spelled backwards in 2 letters. So each 2 letters now, they will denote a single byte, because each is 16, and 16 by 16 is 256. So we'll need 2 hexadecimal digits to denote a single byte. And as we talked before, Intel x86 processors, they're little endian. Not a very self-explanatory term, but what will happen is that the end of that value, so for us this will be FE number, will go at the beginning, at the first address. So this is what we actually see when the file is saved. So FE goes into position 0, and then other bytes follow in sequence. Let's go to see the file that saved the real value. It's also some sort of value. We can look at the hexadecimal representation. For binaries, for real valued numbers, it would be more interesting to see it in the binary, because hexadecimal now doesn't tell us much. In the binary, we would see the Matisse exponent. Right now, we don't really see what's going on in this hexadecimal representation. Okay, so we are done saving just small files. Let's make it big. There's another example right here. and let's look at what it does. So now it opens just one file with file unit 51, just some random number is selected. It has a constant that's called resolution, and it's equal to 100. We are going to write a two-dimensional file of the size 100 by 100. We're not speaking about arrays just yet. We're not holding anything in the computer memory. We're going to just write those bytes in sequence, but we are now have nested do loops where our integer index goes from 1 to 100. That will make it 100 records. And at first we will go sort of like you can think of it as like a horizontal line scan. So for the horizontal line, this would be our I parameter, and for the vertical will be a J parameter. Let's look at what we write. So we first obtain the value from some sort of my function, and then we write this real value into the file using the same write command. The only difference is now we have to give the number of the record so that this value is written in a correct spot in the file. We calculate this number by taking I as the index of the column. We add j minus 1, that would be the index of the row, zero-based index of the row, multiplied by the resolution. So we treat this two-dimensional file as sort of like one-dimensional. We find the index where we should write this number. I know it's somewhat confusing, but it will be self-explanatory just in a moment. Let's look at my function. It's really not a big deal with this function. We are computing a square root of 1 minus x squared minus y squared. This should give us the representation of a sphere, only the part that sort of like a half sphere that goes like above the ground. If we are outside of the sphere, the value is minus 1. So we have minus 1 and then the sphere that sticks out starting from 0 going to 1. It's just something that I decided, nothing particularly special about this function. It's just something that we'll try to somehow plot now. Now that we have saved this file, let's look. It's called test data. What we're gonna do, we're gonna open it in ParaView, the paraview.org. It's version 5.10. Let's open this file. Now, interestingly, we kind of selected a very random type of format, some binary data that contains 100 by 100 values. ParaView knows nothing about it. We will make it, treat it as a raw image data. And to do that, we actually need to change a few things. We will change the extension into raw, not binary, not bin, but raw. And let's do the same thing. Open this in ParaView. Open this file, raw. It will ask open the file with image reader. It doesn't know yet what's the internal components of the file, so we will tell it. First, we select the data type. It's float, little endian. Leave everything here as it is. File dimensionality 2, data extent from 0 to 99. Extent over y from 0 to 99, extent over z doesn't matter because we only have dimensionality of 2. And we will click apply and we get the plot on the right. So this plot, there is a scale at the bottom right. Now the plot shows this sphere as intended. Now it's not really three-dimensional. It's only two-dimensional, but you can already see, I can kind of tilt it, but it's not showing it in 3 dimensions. This is what's called the voxel data, or in our case it will be just like a 2-dimensional discretized data of the size 100 by 100. But I just wanted to show you, because we're doing scientific computing, so this is often used in science. So some raw data just saved without any format, and ParaView can open this using this image reader, what they call it. Of course, ParaView, it has a lot of like different formats. We can actually write into the file what's the dimensionality, what are the saved type of variable. Right here, you can already see that there's a choice between a big endian and little endian. By default, it was actually set to big endian, so we had to change it. There's also a choice between integer types of different sizes, starting from a signed byte that's called here char, or sometimes pronounced car. Short, it means a 2-byte integer. Unsigned short, same thing, just unsigned. Integer would be 4 bytes. Unsigned integer. Then long would be 8 bytes, unsigned long, same thing, 8 bytes just without sign. And then we have float and double. So double will be 8-byte real value, IEEE encoded, as we talked. Float is a 4-byte, which is our standard sort of real variable in Fortran. We are making the pause for now. This lecture is going to be fairly long because it's probably the last one that is recorded on video. So in the previous part of the lecture, we created a way to visualize our binary data. Of course, it would be interesting to use it more, to see what can come out of this newly acquired skill. So let's look at the program with complex numbers now. Complex numbers are not always covered in the programming courses. They're thought of a narrow, strange area of science, although of course they're not. They have a lot of use in science. Let's just start simple. We'll just make 2 complex variables in the program, a and b. By the way, complex numbers are not native type of data to the processor. Every time we do an operation on a complex number in Fortran, the processor will only perform multiplications, divisions, subtractions, additions. Fortran will split those operations as necessary on the real and imaginary parts of those numbers. So typically, CPUs do not crunch complex numbers. Those instructions have to be transformed into instructions for real numbers. Okay, so we have a and b. A will just assign to some complex value. I found later on that putting parentheses like this notation for complex number only works for constants. For if you want to put some variables inside those parentheses, you'll have to call a function CMPLX. There will be a function CMPLX which will create the complex number. We'll first print a, and we will print out the absolute value of a, and then we will print out the values of sine of a and cosine and tangent. I really wanted to print out gamma function of a complex number, but in Fortran there is no gamma function for a complex number. Let's compile, Control S to save. Compile. There's unused variable b. Yes, it is unused. It was used in the previous calculations. And let's look at what we have. So we printed out a as it was initialized. So 1.5 and 3.3. We have the absolute value. You already know how to compute the absolute value of a complex number. we have some numbers as the output of a sine. You know, sine never goes above the value of 1. In this case, it does. It can go to 13.5 and all the way to infinity. Similarly, for cosine, we actually get very similar numbers. Tangent, on the other hand, quite small for its real part and greater than 1 for its imaginary part. All right, you might think, how is this even possible that we can compute the sine of a complex number? What you should know so far is how to add complex numbers and how to multiply them. Let's assume that you already know that. If you don't, pause this lecture, go read about it. There is such a thing that's called Taylor series. Let's look at, and you can already see the illustration on the right is a sine. So the black plot shows the sine function. It is very common to illustrate a Taylor series with the sine. And if you take a polynomial first order, which will be just a linear function, you'll get this red line, which you can see it already approximates sine quite well on a certain range of values. Third order will be the yellow line, and then the fifth order will be the orange line, and so on. For sine, you actually only get terms which are odd, because sine is an odd function. Let's look at the definition of the Taylor series. So if you have a function f of a, the Taylor series is written like this. So f of a would be your constant. You need to pick a, the point around which you will expand the function. You need to compute all the derivatives, as many terms you want in the series. Let's find an example for a sine. There is one here. So a sine would be approximated as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on. The more terms you take, the more precise approximation is. You can also approximate logarithm. In the complex number, you can see separately the real part and the imaginary part. Here are some plots. This is what you'll get for the real part and for the imaginary part. So not super exciting. Of course, if your imaginary parameter is 0, then you just get perfectly normal sine. And it is a periodic function. There is also one way to illustrate complex numbers is to take their absolute value. There's this plot over here which shows absolute value part over the complex plane. The color encodes the angle. There's a way to represent the complex number as an absolute, as a magnitude and an angle. All right, let's look at what we did back in the code. So here we just computed sine, cosine, and tangent of a given constant. We have a much more powerful tool now that we can apply. We can save this into a file and open in ParaView. There is this code. Let's look at what it does now. We have a resolution that's been increased to 1000. We have a real parameter. We have a real constant, pi. So the range in which I want to see the results of my function, I will go from -pi to pi, both for reals and for imaginary parts. and 1000 will be discretization of that range. IDX will be an index of the result in the file. We'll just make it a separate variable to clarify how it works. We will also have some real values, so x and y will be produced from I and j. Those will be our parameter values, but they will be converted into a complex number. Complex number that we will call complex value. And val1, it's a bit of a confusing notation, I must admit. So val1 will be the result. All right, so same as before, open the file, we'll call it sign.raw this time. This time we will have 4 bytes for real and 4 bytes for imaginary. So that doesn't change the parameter over here, but we'll just save those values one after another. As the last time, the index will just start with 1 and will go until the end of the line, increasing sequentially, and then just continue with the next line and continue with the next line and so on. The index is based on starting with 1. Then we evaluate the sign. This is the main part of our calculation. Split it back into real and imaginary using the functions real and aimag, aimag. If you're still unsure about this function, you can read about it in the reference for Fortran, but it just pretty much it takes out the imaginary part and supplies it as a real value. And we write those into the file. The only small trickery over here is that we will write them in sequence. We take our index and we use the index, but at this index we'll write the first value and the second value. It takes a little longer than the previous one. Actually, it tells you that it took 4 seconds to run. ParaView as the same as the last time. Open the raw file with the image reader. Right now, we don't see anything because we need to tell it. There's going to be floats, little endian. Now there are 2 scalar components, 2 dimensions, from 0 to 999, from 0 to 999, and apply. Oh, by the way, let's do a few more things. So in this filter, so that's the import filter in ParaView. There are more options, coloring. Let's just change it. On the right, I can select just some other options to present it. This seems to have a very high contrast. And we will look, right now it shows magnitude, but we can see, okay, so now it properly works. All right, so we have components for the real portion x that I can select. X, it thinks of x as just like a first variable in the file. We told it that it has 2 components, and it just automatically sort of names them x and y. So x is the real part, y is the imaginary part, and it can also show it as a magnitude. This is the illustration of the complex sign function. Fairly interesting. We're already getting into the area of scientific computation where it's getting closer to how scientists see those things. There's an article about gamma function. And interestingly, I remember that article had an amazing plot of its complex values, and of course there's many new plots of the complex values, but there was one that goes back quite some time. So it's a hand-drawn graph of the absolute value of the complex gamma function from tables of higher functions. I don't know what the year of that. That's very curious, actually. Let's see. Almost sure that they did not have computers when they plotted that. So people were mathematicians and scientists from other fields that were already interested in complex values of gamma function back then. For some reason, maybe even for some practical reasons, that it's actually applied somewhere in science. Unfortunately, again, if we look at the intrinsic procedures in Fortran, let's look at cosine, for example. It allows you to supply a parameter as real or complex. So here, arguments, the type shall be real or complex. So it takes complex arguments. For gamma, compute and only type real, and neither a zero nor a negative integer can be supplied. So that concludes lecture 9.